Okay, our first real chapter is on matter. Now, matter you may have a definition of already from middle school, but we are now going to look at matter more closely because matter is what we study in chemistry. So normally in class I would ask the question, what is chemistry, and then wait for you guys' response. But since this is a remote learning tutorial for those of you who are not in class, the question is, what is chemistry? And the answer is, chemistry, for our definition and for our class, is the study of matter, its structure, properties, and composition. And as important, the changes that matter undergoes. So the first question you should ask is, well, we're studying matter. What is matter? Matter is anything that has mass and occupies space. In other words, it has a density, and sometimes refers to it as the stuff that the universe is made up of. Now, what do we mean by mass? Mass is a measurement of the quantity of matter. Remember back in the first chapter, the review chapter, we talked about making good measurements, and mass is a measurement that you can make to describe the quantity of matter. Now, here's the thing that you may or may not know about mass. Mass is not affected by its temperature, location, or any other factor known to alter a measurement's value. So, for example, a mass of something on Earth is the same thing as the mass on the moon. The mass of something in Melrose, Boston, is the same as it is in Los Angeles. If I took a block of aluminum and left it in your house, air-conditioned house, and measured the temperature, it might be 30 degrees C. If I took it outside on a warm, hot summer day, the temperature would change to like 40 degrees C, but the mass does not change. So if you are new to some of my tutorial lessons, a lot of times I will ask you to do a little bit of work during the tutorial to make sure that you're understanding the concept. And this is one of those times. So what you're going to do when I tell you to is you're going to stop the video. Tell me if these items here are matter or not. You can either write yes or no. And then when you're ready to get the answers, start the video again and I will go over the answers. So your question you're going to ask is, does these things or do these things have mass and volume? If they do, then they're matter. If they don't, they're not. So when you're ready, stop the video and then do the problems and then restart the video. So stop the video now. So here are the answers, and I'm just going to make one simple comment on this. You can look at the answers and read the text just as well as I do. But when we talk about things like energy, electricity, heat, they are always going to be not matter. Any energy sources, nuclear, solar, electricity, thermal, any type of energy has no mass and it doesn't have any volume. We can measure the quantity of energy, but we don't measure the mass of energy or the volume of energy. The other one here is pressure. Pressure is a force over a unit area, and forces, again, do not have mass. So everything else on here has some type of mass and volume, and therefore would be considered matter. In previous science classes, you were taught and possibly learned that there are 3 states of matter. Actually, there are 4. And the last one is plasma. Plasma is just basically a highly charged, rapidly moving gas. But plasma is not a phase of matter that we are going to be concerned with in this high school chemistry course. So we're going to go back to the ones that you probably are very familiar with, solid, liquid, and gas, right? Now, in this particular case, we're going to have some more definitions to what these phases are from more of a micro or particle scale type of definition. And so that's what we're doing here. In a solid, the particles are close together and they don't move. They just vibrate in place. In a liquid, particles are still close together. Actually, they're very close together, but there is some sliding and moving of the particles. That's why you can get flow in a liquid, because the particles are flowing over each other. In a gas, the particles are very far apart. Actually, most of the gas is empty space, and there's a lot of rapid movement. So we're going to start to talk about these phases more on a particle energy type of scale. So I'm sure some of you have seen these particle models of matter before. And then in this case right here, all of these models have the same number of particles in them, but they all look different, right? Here's my solid. It has a fixed shape and fixed volume. The liquid has a fixed volume. It's the same volume as this. It doesn't look like it, but it is. But it does not have this fixed shape. And then the gas has a much larger volume, because most of the gas is this empty space here, right? Now, if you talk about motion, there is no motion here. In other words, the particle does not deviate from its location. What it does do is it vibrates. It vibrates in its location, but it doesn't change its location. In a liquid, you do have slight changing of location. So these things do move a little bit, right? And you would represent that by these little arrows, right? So over time, the particles in the water move, or let's say water, the particles of a liquid move from point A to point B over time. In a gas, the particles move very rapidly and very far. They have the highest energy, right? So there's no movement in the solid, some movement in the liquid, lots of movement in the gas. And the gas has a lot more free or empty space. If you look at the space in between the particles here, it's very, very small, very little. Same thing here. Lots of open space here, very little open space here, very little open space here. And we call that open space free volume. So this is just a summary of all the aspects of each phase from a particle standpoint, right? A particle standpoint. Now, you're going to have to know this, because this is what's going to be able to describe each one of your phases from a particle model standpoint, and also help you understand why the properties of a material are when they are in each one of these phases. Now, the thing to take away from this also is this particular expression. The kinetic energy, particle motion, free volume, distance between particles, and compressibility are all the lowest in the solid. As you increase from a solid to liquid to gas, those same parameters are highest here. That's why a gas is very compressible. It has a lot of free volume, it has a lot of kinetic energy. The liquid, on the other hand, is not compressible, because it does have very minimal free volume. And so does the solid. Very minimal free volume, so it's not compressible. Which brings me to a point about the liquid. One of the properties of a liquid that's cool is that it flows, but it can't be compressed. So if you've ever been to a car repair shop, a hydraulic lift that you put your car on to lift it up so the workers can work underneath it is all done because of hydraulic lifting fluid, because a fluid can flow into the piston, but it doesn't compress. And so putting a force, large force behind it is able to lift your car, because you're not compressing the liquid, you're actually pushing the liquid up into the piston, and that piston then raises your car. If you tried to do that with a gas, you would compress the gas, and the gas wouldn't lift the piston. So again, here's one of those quick reviews. So what you're going to do is you're going to look at these items here, and you're going to characterize them either as a solid, liquid, or gas. Now, some of the items could fit under both solid and liquid, liquid and gas, or maybe all three, right? You have to choose which ones that it fits under. So, for example, If it says generally has the highest density and you thought that it would be with the solid and liquid, you would put an X on both sides. All right. So what you're going to do is review this real quick, stop the video, answer the question by putting a little X or something on your piece of paper, and then restarting the video when you're ready to get the answers. So stop the video now. Okay, so here are the answers. You can self-check them if you want. Just a couple of quick things. When we talk about compressible, we talk about things that you can compress and change the volume of that material considerably. You cannot do that with a solid or a liquid, right? You may think you'd be able to do it with a solid or a liquid, but you can't. A gas is the only one that's really compressible. Some of these other ones have multiple entries, defined volume, that's both a solid and a liquid. Particles move and change location, that happens in a liquid and a gas. And then particles are closely packed, that's a liquid and solid. Solid and liquid. So there you go. All right, so make sure you understand these. This could be a type of quiz question that I could ask you in the future. Now that we have an understanding of what matter is and the phases of matter and how to describe the phases of matter from a particle standpoint, the next thing we want to be able to do is to classify matter beyond its state of matter. So in other words, yeah, we know it's a solid, liquid, and gas, but what else do we know about it? And this is where we're going to better describe using material properties. And the better you can describe a material's properties, the better you can understand its performance in an environment, and also you're able to design with it. So let me explain what that means. If you wanted to have a material, design with a material to operate in an environment underwater, you don't want to have a material that's going to easily dissolve or easily corrode underwater. If you wanted a material that's going to operate in a very high temperature environment like in the furnace, you definitely don't want to select a material that's going to have a low melting point. So by understanding the properties, now you have a better understanding of how the environment's going to handle this material, and you can design with it. So the material properties that we considered are mechanical, chemical, physical, electrical, and thermal. The ones we are most interested in for this particular class will be chemical and physical, some thermal, and some mechanical. Now this chart's pretty busy, but what I'm trying to show you here is when we classify a material's property, here's my material, we can break it down into physical, chemical, electrical, thermal, and mechanical. I haven't listed any sub properties for mechanical because there's not enough room in here, and we're really not that much interested in it. But if you took a mechanics course, you would see that things like yield strength, tensile strength, modulus of elasticity, all those things would fit under mechanical. The ones that we're mostly concerned of are these: conductivity and resistivity, conductivity for electrical. So physical, we have the phase, hardness, how hard is something, as far as can you push your fingernail into it easily. If it's very hard, you can't. If it's not hard, it's very soft, you can. So think of like wax and then like metal. Boiling point, melting point, density, whether a chemical is an acid or a base, its reactivity in oxygen or against flame or anything like that. Solubility, does it easily dissolve in water? Does it easily dissolve in an organic solvent? And then flammability, does it easily burn or does it blow up? Okay, so this is what we're going to be using for the rest of the year, some of these properties, and you're going to learn about those. So if you remember back to the definition of chemistry, one of the parts of that definition was the study of the changes occurring in matter. And so we're going to talk about those changes now. There are two types of changes that we're going to be concerned with for this class. There's a physical change, and then there's a chemical change. So physical and chemical. In a physical change, what you start with as far as the material is what you end up with as far as the material. But the material has a change in appearance. So the appearance changes, but the composition of the material remains the same. So you still have, let's say, paper at the end of the process. So if I take a piece of paper and I crumple it up, the appearance of the paper has changed, but I still have that piece of paper. In a chemical change, I'm actually changing the material into something new. So a chemical change, you get a new material. And let's go back to that piece of paper. If I took that piece of paper and I crumpled it up, that would be a physical change. But if I took that crumpled piece of paper and then lit it on fire, I would have a chemical change. Because at the end of the day, the new material that I make when I burn paper is not the same as I did when I first started with the crumpled paper. I can't get that crumpled paper back after I burn it. I've made something new. So that's the difference. Physical change, you have the same material composition at the start versus the finish. Chemical change, you make a new material. Here's one of those stop and do activities that we're doing in the lesson. So in a minute, I'm going to ask you to stop the video, look at these processes or actions, tell me if it's chemical or physical change. Remember, if it's a physical change, you have the same composition of material at the end as you started with. If it's a chemical change, you've made a new material. The composition of the new material is different than the starting material. So look these over real quick. Stop the video and I tell you to in a second. Put chemical or physical change and then start the video when you're ready to check it. So stop the video now. So here are the answers. One piece of helpful information: any phase change is a physical change because you are not changing the composition of matter between each state. Frozen H2O is the same H2O as liquid H2O. So if you were to melt something, you go from the frozen state to the liquid state, that doesn't change that it's H2O. Okay? Cooking an egg, anything like cooking, baking, frying, burning, rusting, corroding, oxidation, tarnishing, those are all examples of chemical changes because you make a new material at the end of that process. Okay? So things like that are going to be considered chemical changes. Things like mixing, melting, all those things are just physical changes. So the last concept that we're doing today is intensive versus extensive properties. Now, properties that you describe them can either vary with the amount of material or not. And that's what extensive versus intensive property means. A property that varies with the amount of material is an extensive property because it depends on the amount of material. So these were things like volume, mass, weight, length, right? If I add more material, does the mass change? Yup. If I add more material, does the volume change? Yup. If I cut the volume in half, does the mass change? Yup. An intensive property is a property that doesn't change with the amount. So things like melting point, boiling point, color, density, right? Nobody's ever said to you, what is the melting point of water? And you say 0 degrees C, but then you say, oh, only if it's less than 500 grams. No, you never say that, right? Because it doesn't matter how much water you have. Water always melts or freezes at 0 degrees C. Same thing with the boiling point. It's always boiling or condensing at 100 degrees C. It doesn't matter how much you have. Now, the one that sometimes trips up students is color. And they say, well, if I take a little drop of yellow food coloring and I put it in a glass of water, it's very light yellow, but if I add more drops, it gets very dark yellow, so the color changes. Well, the color is not actually changing. The intensity of the color is changing. And the better example is this. If I take a green crayon or a yellow crayon or whatever crayon color you like, and I make a line on a piece of paper, and then I cut that crayon in half, and then I take one of the halves and I draw a line again, does the color match? And the answer would be yes. So it doesn't matter how much you have. The color of something is not going to change with the amount of it that it has. So again, extensive properties vary with the amount, intensive properties don't vary.